Hello everyone, I am Dr. Merchant and it is my pleasure to welcome you to this introductory session on mathematics behind the intelligent machine, and thank you to joining me. Let me begin with a small story. Think about the first thing when you wake up and unlock your mobile phone. It recognizes your face instantly. It suggests messages while you type. It recommends content that you feel surprisingly accurate. To us, it feels intelligent, almost human. But there is a real question. How does the machine know what to do? The machine does not see a real face as we do. It does not understand the language like a human do. What it sees are the numbers, what it processes are the patterns, and what drives every decision behind the scene is mathematics. This is where our journey begins. Behind every intelligent machine lies a quiet but powerful story of vectors combining information, equations adjusting themselves, errors being measured, and solutions improving step by step. What appears as intelligent is in reality learning guided by mathematics. In this module, we will uncover that story. We will explore how linear algebra help machine structure data, how calculus enable them to learn from the mistake, how the probability and statistics allows them to deal with uncertainty, and how optimization techniques push them towards better performance. This session is meant to give you an overview. It is not about memorizing the formulas, but about understanding why mathematics is essential to intelligent system. As we move forward, you will see that machines do not become intelligent by chance. They become intelligent because mathematics teaches them how to learn. With this thought, let us begin our exploration of the mathematics behind the intelligent machines, and once again I welcome you to join this session. When we talk about the advanced technologies, we often focus on tools, software or hardware, but if we think deeper, we find a single engine driving all of them is mathematics. Every line of the programming is built on mathematics logic. Every AI model learns by optimizing mathematical functions. Machine learning improves through statistics, probability, and calculus. When you see the smooth visual in movies or the games, they are powered by graphic algorithm based on geometry and linear algebra. Game engine and simulations rely on mathematical models to repeat motion, physics, and realism. Signal processing uses mathematics to clean, compress, and transmit information. Robotics combines algebra, calculus, and control theory to enable movement and decision making. Cryptography protects data using number theory and complex mathematical structure. Even blockchain technology is secured by the mathematical hashing and cryptographic proofs. Different technologies may look unrelated on the surface, but at their core, they all speak the same language, the language of the mathematics. This is why to understand intelligent machine, we must first understand the mathematics that powers them. To understand why mathematics powers artificial intelligence, we need to understand one simple fact. AI learn from the data, and data is numerical. Mathematics provide the framework that allows machines to represent the data, learn from it, and improve their prediction over the time. Without mathematics, AI would have no way to understand pattern, measures error, and decide what to improve. Let us look at the mathematical pillars behind AI. Linear algebra gives a structure to the data, and it allows machines to represent input, weight, and output in the form of vectors and matrices. Next we have is the probability theory that helps AI images uncertainty and makes informed decision when outcomes are not certain. Calculus enables learning by showing machines how to adjust their parameters to reduce errors. Optimization derives improvement, helping models find the best possible solution among millions of the possibilities. Pattern recognition allows the AI system to detect similarities, trend, and structure hidden in the data. Data analysis transforms raw data into meaningful insight. Prediction uses mathematics model to estimate future outcomes. And finally, learning capabilities emerging when all the mathematical tools work together. What we call intelligent in the AI is actually the result of these mathematical processes operating in harmony. This is why mathematics is not only In AI, it is foundation on which intelligence is built. When we talk about artificial intelligence, it is not just a concept for the future, it is already at work around us. In healthcare, AI help doctors detect disease earlier, analyze medical images and precision, and recommended personalized treatment plans. These decisions are driven by the data pattern and mathematical models working behind the scene. In finance, AI system detect fraud, assess risk, predict market trend, and automate decision making. Every transaction is evaluated using probability, statistics, and optimization technique. In education, AI personalizes learning experience, evaluates student performance, and supports intelligent tutoring system. It helps institutions make informed decisions and based on data-driven insight. Across industries, AI streamlines process, reduces human error, and enhances decision making. What enables all this transformation is the ability of machines to analyze large volume of the data, recognize patterns, and learn from experience. Once again, at the core of this revolution lies mathematics, quietly powering intelligent decisions in the real time. To build and understand intelligent machine, we need a core mathematical toolkit. Each tool play a specific role in how AI system learn, reason, and make decisions. Statistics help us make sense of the data. Through descriptive static, we summarize and understand what the data look like. Through inferential statistics, we draw conclusion, make prediction, and measure confidence in the result. Linear algebra is the language of neural network. Vector operations allows machines to represent input and features. Matrix operations enables the transformation of the data as it flows through layers of the neural network. Probability allows AI to work in uncertain environment. Probability distributions model randomness and variability in data. Bayesian inference help system update their beliefs as new information becomes available. Calculus is what makes learning possible. Differentiations tell model how to reduce errors and improve performance. And on the other hand, integrations support accumulation, expectation, and continuous modeling. Together, these mathematical tools form a foundation that allows machines to learn from the data and act intelligently. At the heart of every neural network lies linear algebra. It is the mathematical framework that allows machines to store, transform, and learn from the data. Let us look at the key pillars of linear algebra that supports intelligent system. Very first we have is the vector space that provides a structured way to represent the data, where each input such as an image, a sound, or the text can be expressed as a vector of the numbers. Systems of linear equations help machines solve multiple relationships at the same time. In a neural network, these systems describe how input and weight interact to reduce in outputs to produce outputs. Matrices act as the engine of the computation. They store weight, transform data between layers, and enable efficient processing of the large scale information. Linear transformation describe how data changes as it moves through a network, how it is scaled, rotated, or projected into new spaces to reveal patterns. Determinants provide insight into matrix behavior, such as whether transformation preserve information or collapse it. Finally, eigenvalues and eigenvectors reveal the most important direction in data. They help identify dominant pattern and play a key role in dimensionality reduction and feature extraction. Together, these concepts make linear algebra the backbone of neural network and modern AI system. To machine, data does not exist as a vault, images, or the sound. It exists as a vector. A vector representation converts real world information into numerical form, allowing machines to process and learn from it. Through data transformation, raw input are converted into the structured vector that a model can understand. These vectors are help in capturing relationships, showing how different features related to each other with the data. In multiple dimension space, each dimension represents a feature and every data point becomes a position in that space. Patterns emerges based on distance, direction, and angle between vectors. This representation is not just about the structure, it directly enhances performance. Well-designed vector representation lead to faster learning, better accuracy, and improved generalization. Finally, vector representation facilitates analysis by making complex data measurable, comparable, and mathematically manageable. In simple terms, vectors are how machines see and understand the world. When data grows large and complex matrices becomes the most powerful tool for the handling. It in machine learning, almost every computation is the matrix operation. Matrix addition allows models to combine information such as adding biases term during the learning. Matrix multiplication is the core operation of the neural network. It consists input to the weights and produce output at each layer. Matrix inversions play an important role in the optimization and solving system of the equations, especially in classical machine learning method. These operations are not abstract, they directly enable real-world applications. In neural network language processing, word and sentences are represented as matrices that capture meaning and context. In image recognition, pixel values are recognized into the matrices, allowing machines to detect edges, shapes, and patterns. During neural network training, matrix operations allows millions of the parameters to be updated efficiently and simultaneously. By visualizing these matrix calculations, we begin to see how machines process information at scale and speed. In short, matrices are the computational engine that make machines learning practical and powerful. Artificial neural networks are built almost entirely on the linear algebra. Every component of a neural network, input, weight, biases, and output can be represented using the vector and the matrices. The structure of the neural network is defined by the matrix connections between layers. These matrices control how information flows from input to output. Through data transformation, input are multiplied by weight, matrices are shifted by bias vectors, creating new representation at each layer. Learning and optimization occurs when these matrices are updated to reduce error. Gradient-based methods adjust matrix values so that network performs better over time. Linear algebra also enables analysis and interpretation, helping us understand how features influence output and how representations evolve across layers. Most importantly, it allows a neural network to model complex relationship patterns that are too intricate to capture using the simple rules. In essence, linear algebra is not just a support tool of our artificial neural network, it is the framework that makes neural network intelligence possible. If linear algebra gives the structure to neural network, calculus gives them the ability to learn. Calculus helps machines understand how small changes in the parameter affect performance through this. Models learn from the mistake and improve step by step. Different models follow a diverse learning style. Some learn quickly, some slowly, and some adapt continuously. Calculus guides them learning behavior by controlling how adjustments are made. Using computational tool, calculus allows machines to calculate gradient efficiently even in every large network with millions of the parameters. This creates a dynamic learning environment where models continuously update themselves and new data arrives. Finally, learning algorithms such as gradient descent, backpropagation, and optimization techniques are all rooted in the calculus. These algorithms tell machines how to move towards the better solution. In simple terms, calculus is what turns a static model into the learning machine. To understand how machines learn, we first need to understand the idea of derivative. The derivative tells us the slope of the curve, where it is steep or flat. A steep slope means rapid change, while a flat slope means little or no change. This idea appears across mathematics, physics, and in engineering. It helps us describe motion, growth, decay, or automation. In AI, it tells a model how fast and in which direction it should learn. The derivative is visualized using a tangent line at any point on the curve. The tangent line touches the curve at exactly one point. The slope of this tangent line represents the derivative at that particular point. This slope describes the rate of change of a function. It shows how the output responds when the input changes slightly. By understanding this behavior, we can make prediction and control outcomes. In machine learning, derivatives guided a model towards the better performance by showing how to reduce error efficiently. Simply put, derivatives teach machines how to move, how fast to move, and when to stop. Once we understand the derivative, the next step is the gradient descent, the method that actually trains the model. Imagine standing on a hill covered in the fog and trying to reach the lowest point in the valley. The only information you have is the steepness of the ground beneath your feet. The safest way down is to move in the direction of the steepest descent. This is exactly how gradient descent works. The loss function represents the height of the terrain. It measures how far the model's predictions are from the correct answer. The gradient tells the model which direction lead downhill towards the lower error. There are different forms of the gradient descent. First is base gradient descent, which uses the entire dataset. Second one we have is the stochastic gradient descent, which update parameters using one data point at a time. Mini batch gradient descent, which balances speed and stability. During parameter update, model weight are adjusted step by step in the opposite direction of the gradient. Each step brings the model closer to optimal performance. Through repeated update, the model gradually reaches convergence, where improvement becomes minimal and learning stabilizes. This process is core of the model training, transforming an untrained system into an intelligent one through mathematics. For a machine to learn, it must first understand how wrong it is. This is the role of the loss function. A loss function measures the difference between the model's prediction and the actual outcome. It turns errors into numbers that can be analyzed, compared, and reduced. The importance of loss function lies in the two key areas. First, model performance, and second, task stability. The right loss function ensures that the model focuses on that truly matters for a given problem. Loss function guide automation during the training process. They provide the signal that gradient descent uses to adjust parameter and improve accuracy step by step. Different task requires a different loss function. Mean squared error is commonly used for regression problem, where predicting exact value is important. Cross entropy loss is widely used in classification tasks, where probability and decision boundaries matter. By visualizing prediction errors clearly, loss function transform mistake into the learning opportunities. In simple terms, loss function tell a model how well it is doing and how much it needs to improve. Probability and uncertainty, making decisions under uncertainty. In the real world, outcomes are rarely certain. This is where the probability becomes essential. Probability help us visualize the distribution of outcomes. Instead of giving a single answer, it tells us how likely different outcomes are. In AI system, probability plays a key role in risk quantification, informed decision making, and data analysis. It allows machines to choose the most reliable option when complete certainty is not possible. Probability is measured of a likelihood, always ranging between 0 to 1, and where 0 means impossible and 1 means certain. Uncertainty, on the other hand, arises from unpredictable outcomes or incomplete information. Data may be noisy, missing, or evolving over time. AI system must operate effectively despite these limitations. By modeling uncertainty using the probability, intelligent system can make balanced decision rather than absolute guesses. In short, the probability teaches machine how confident to be or not just what to predict. In classification problem, the goal is not just to assign a label, but to understand how confident the model is about that decision. Probability help us visualize the classification outcome by assigning likelihood to each possible class instead of making a single hard choice. This supports better decision making. When a model knows how confident it is, it can make more informed choices, leading to improved accuracy and reliability. Probabilistic model uses statistical technique to estimate the likelihood of each class based on observed data and learned pattern. These probabilities allows for confidence measurement, helping us evaluate prediction accuracy and reliability of results. For example, a prediction with 95% confidence is far from trustworthy than one with 55%. Through data categorization, features are analyzed and mapped to distinct classes such as spam or not spam, disease or healthy, or object categorized in the images. In essence, probability transform classification from the guess into the measured confident decision. Statistics plays a critical role in the machine learning by helping us understand the data, evaluate models, and make informed decisions. In model evaluation, statistics shows us to measure validity, whether a model is correct and reliability, whether it performs consistently across different dataset and the conditions. For data understanding, statistical method help with the pattern identification, relationship assessment, and uncertainty quantification. They reveal trend, correlation, and variations hidden within the data. During the algorithm development, a statistic guide the creation of a predictive model. It helps select features, compare models, and decide which approach is most appropriate for a given problem. By grounding machine learning in statistical reasoning, we ensure that predictions are not only accurate but also meaningful and dependable. In short, statistics turns raw data into the evidence and evidence into intelligent decisions. Once a model is defined and evaluated, the next challenge is improvement. This is where optimization techniques come into play. Gradient descent is the most widely used optimization method. It iteratively adjusts model parameter to minimize errors and move towards optimal performance. In reinforcement learning, automation happens through interaction with the environment. The model learns by maximizing reward and minimizing penalties over time. Data leverages focuses on the making the best use of the available data through feature selection, data weighing, and efficient sampling to enhance learning effectiveness. Genetic algorithms take inspiration from natural evolution. They optimize solutions through selection, crossover, and mutation, making them effective for the complex and non-linear problem. Finally, parameters fine-tuning refines learning by adjusting the hyperparameters such as learning rate, base size, and regularization strength to achieve better accuracy and stability. Together, these techniques ensure that learning systems do not just work but work optimally. As the model learns, it begins to separate data into the meaningful group. This separation is defined by the decision boundary. A decision boundary is the line, curve, or the surface that divides the different classes in the feature space. It represents how a model distinguishes one category from another. By studying decision boundaries, we gain insight into how a model makes decisions and which feature influence those decisions. Decisions boundary also help identify the pattern in the data, revealing whether classes are clearly separable or overlapping. Well-shaped boundaries improve performance by reducing the classification error, while overly complex boundaries may lead to overfitting. Most importantly, effective decision boundaries ensure generalization, allowing the model to perform well on new unseen data. In essence, the decision boundary is where mathematics becomes a decision. Geometry plays a vital role in how intelligent machines perceive, understand, and interact with the world. In robotics, geometry helps machines navigate space, plan motion, and avoid obstacles. In computer vision, it enables the system to recognize shapes, depth, perspective, and object boundaries. In natural language processing, geometric representation allows the meaning of the words and sentences to be mapped in high dimensional space. Within machine learning, geometry enhances algorithm by improving pattern recognition and defining distances, similarities, and separation between data points. Spatial reasoning allows the AI system to understand relationship such as proximity, orientations, and structure, making decisions from intuitive and reliable. Finally, geometry supports the data visualization, helping to interpret complex data, high dimensional data, and making more accurate prediction. In essence, geometry gives AI a sense of space, turning abstract data into the structured understanding. Artificial neural networks are not built on a single mathematical idea. They are the result of multiple mathematical concepts working together in harmony. At the heart of every A and N is its structure. Neurons connected through weight link. These connections define how information flows through the network. Linear algebra gives structure to this flow by representing input, weights, and output as vector and matrices. Calculus enables learning by guiding how weights are adjusted to reduce the error. Statistics and the probability help model handle uncertainty, evaluate performance, and make reliable predictions. Activation functions introduce non-linearity, allowing network to capture complex pattern that linear model cannot. Without activation function, neural network would be able to model real-world complexity. During the training, weighted connections are continuously updated through automation technique to improve the performance. Each update is mathematically guided, ensuring the network learns efficiently. In summary, an artificial neural network is where mathematics becomes intelligence, structure learning, and uncertainty and automation allow all working together to solve the complex problem. Forward propagation describes how information moves through the neural network from input to the output. The process begins at the input layer, where data features are combined using the weighted sum. Each neuron then applies an activation function, transferring this sum into output signal. This output becomes an input to the text layer. As data flows from the network layers, each neuron's process will form in the same way. Weighted sum followed by activation, gradually building more meaningful representations. At the final layer, the network produces its output, such as prediction or the classification. This output is then compared with the actual result using the loss function. The loss function measures how far the prediction is from the desired outcome, providing feedback of the learning. In simple terms, a forward propagation is how neural network thinks forward, step by step, turning raw data into the meaningful data. Once a neural network makes a prediction, the next question is simple: how can it do better next time? This is where propagation comes in. Propagation starts with the error minimization. The model compares the predicted output with the actual output and measures the difference using the loss function. Next comes gradient calculation. Using the loss function and the chain rule from the calculus, the network compute how much each weight contributed to the error. These gradients guide weight update. Each weight is adjusted slightly in the opposite direction of the error through an iterative process. With every iteration, the network reduces its error and improves performance. This cycle of the prediction, error, measures, and adjustment continues until the model learns effectively. In simple terms, propagation is how a neural network learns from its mistake. Training a neural network is a structured and systematic process, not a single step. It begins with the data preparation. Raw data is cleaned, organized, and formatted so that the network can understand it. Good data preparation is critical for effective learning. Next, we define the architecture of the network, deciding the number of layers and the number of neurons in each layer. This structure determines the model a capacity to learn pattern. The training process then begins using the forward propagation. The network makes prediction using propagation and automation algorithm. It adjusts weights to reduce error. Throughout, training performance monitoring is essential. Validation data help track learning progress and prevent overfitting, ensuring the model generalization well. Finally, the trained model is tested using evaluation data. Performance metrics such as accuracy are used to assess how well the network performs on unseen data. This step-by-step process transforms an untrained model into intelligent system. At this point, a common question arises: how much mathematics do you really need? At this point, this question is arise: how much mathematics do I really need to learn AI and neural network? The answer is reassuring. You do not need to master all of the mathematics. What you need is a working understanding of the key concept. Statistics help you analyze the data, draw inferences, and evaluate model performance. Linear algebra allows you to work with the vectors and matrices, the building blocks of the neural network. Calculus teaches machine how to learn through derivatives, and where needed, integrals probability help models handle random uncertainty and data distribution. The focus is not on the complex proof but on understanding how these tools work together in the practice. With consistent engagement and concept-based learning, mathematics becomes an enabler, not a barrier. This module is designed to help you build exactly the level of the mathematical understanding needed to work confidently with the intelligent machines. Along with you need just like a computing tool, and Python is very essential if you are want to build your career in AI and machine learning. So you must adopt and learn Python. And during this course, along with all the mathematical basic concept, we will teach you Python basic to advanced for the AI and machine learning. As we conclude this module, let us reflect on the key takeaways. Mathematics provides the foundation for every we have discussed, from data representation and learning algorithm to automation and decision making. Understanding these concepts help us visualize how intelligent systems work rather than treating them as black box. The impact on industries is already visible in healthcare, AI support diagnosis and treatment planning. In finance, it enables risk assessment and fraud detection. In education, it personalizes the learning. In manufacturing, it improves efficiency and automation. With this impact comes a responsibility. Ethical considerations such as bias, privacy, and accountability must be addressed. Mathematical models reflect the data they are trained on, and making ethical awareness essential in the AI development. Looking ahead, the future of AI points towards explainable AI, autonomous system, and continued AI-driven innovations. These advances will rely on every more heavily on the strong mathematical foundation. In closing, mathematics is not just a subject behind AI, it is the reason intelligent machine exists. Thank you for your attention, and I wish you success as you continue your journey into artificial intelligence and machine learning. Along with I would like to inform you about the course. Every journey into artificial intelligence begins with a single step: curiosity. What you have seen today is only an introduction and inspiring glimpses into how mathematics shapes intelligent machine and drives modern innovation. This is an invitation to go deeper, to explore how artificial neural network and machine learning are designed, trained, and applied to the real world problem. Our certificate course on artificial neural network and the machine learning is structured to guide you step by step from foundation concept to the practical understanding, making AI accessible, logical, and impactful. If you are ready to transform curiosity into the capability, if you want to be part of the next generation of the intelligent system, your journey begins here. Please, you can scan the QR code below to learn more and enroll. Thank you, and we look forward to welcome you to the course.